Now we'll say, even though tree diagrams and other visual aids give you a really reliable way of counting the number of ways that these kind of things can be done, these tree diagrams are not really practical when the number of ways to do something gets really large. So what you'll find is that you'll want to have some better ways of doing these things when the number gets large. Now that doesn't stop you from picturing a tree diagram in your mind as you're thinking about it, and I often do that, but the actual drawing of the tree diagram becomes impractical when you get branches that run into the hundreds or even the 50s. So that's what we want to do now, sort of looking at a better way of doing problems where the number of branches would just be too large to practically do it that way. And the idea is to just look and think about what a tree diagram is telling us so that we can figure out a way to avoid having to actually draw it out all the time. Doing that leads us to something called the fundamental counting principle. I'll call it FCP sometimes, just to shorten the words. And here's what the fundamental counting principle says. It says a task composed of a series of subtasks in which the first subtask can be performed in A ways, the second subtask can be performed in B ways, the third subtask can be performed in C ways, and on like that. The task itself can be done in A times B times C, and you just multiply all the number of ways for the subtask together, and that product is the number of ways the whole task can be done. That's a little awkward to say, so it's probably good to just think about what it really means by doing some examples. So let's go back to the problem that we started this discussion off with, that problem about the coin flips, where we've got a penny, a nickel, and a dime. We flip the penny first, then the nickel, and then the dime. You remember that problem? Let's go back and apply the fundamental counting principle to that. Remember, we found those 8 possibilities. I've got them listed there on the right, but we've done this before. The difference is, here we're going to try to apply the fundamental counting principle and see how much easier it is to get 8 than drawing out that tree diagram, although with 8, the tree diagram is a viable method of doing it. So what I do is I look at this as a product of 3 things. The number of ways of getting a result when I flip the penny, the number of ways for getting the result when I flip the nickel, and the number of ways to get a result when I flip the dime. And the product of those 3 numbers will be the number of ways that we found earlier. So thinking about this, there are only 2 ways to get a result for the penny. It's either head or tails. There's only 2 ways for the nickel, head or tail. There's only 2 ways for the dime, head or tail, and 2 times 2 times 2 is 8. And although you're not listing the actual 8 possibilities, if you're just trying to find out how many possibilities there are, this is certainly much faster. And you can imagine how much faster it would be for the one with 16 branches, or one with 64 branches, or 1,024 branches. It gets impractical to draw the tree diagram, and even when it is practical, if you're just looking for the number, it still may be easier to do it by the fundamental counting principle. Here's another one. Using the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, how many 6-digit numbers can be constructed if 0 can't be the first digit and the digits may be repeated? You can repeat digits, but you can't start off with a 0. Fundamental counting principle says if you can break that down into a series of subtasks, the subtask would be choosing each digit. And since there are 6 digits, you would have a product of 6 subtask counts. So if I'm looking at the first digit, they've already told me that the first digit can't be a 0. I can choose anything else, but I can't choose a 0. Well, there are 9 digits that aren't 0. So there are 9 ways to do that. But when I get to the second digit, since digits can be repeated, I can use not only the 0 this time, but I can use whatever the digit was chosen first, because I can repeat them. That means all 10 digits can be used for the second digit, but not only the second digit, the third, fourth, fifth, and sixth digits. So I can use any of the 10 digits for the second digit, any of the 10 digits for the third, for the fourth, for the fifth, and for the sixth. And by the fundamental counting principle, the number of ways to construct that 6-digit number with these restrictions is simply 9 times 10 times 10 times 10 times 10 times 10, which comes out to be 900,000. So there are 900,000 different ways to write down a 6-digit number that can't begin with a 0 but may have repeated digits. There's no way you could draw a 900,000 branch tree diagram. Another problem. Using the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, just as before, how many 6-digit numbers can be constructed? Same sort of problem, but there are different conditions. This time the number must be odd, it must be greater than 600,000, and the digits may be repeated. So it's still a 6-digit number, so you're going to have the same setup in the previous problem. You're going to have each subtask being choosing a digit, and there's 6 of them, so it'll be a product of 6 subtasks. This time, though, the number has to be odd and greater than 600,000, and the digits can still be repeated. Let's begin by dealing with the greater than 600,000 issue. If you think about it, numbers greater than 600,000, you could have 600,001, you could have 750,000, 800,000, 976,000, 492, things like that. In other words, that leading digit could either be a 6, a 7, an 8, or a 9. So just think about this a minute. It could either be a 6 or a 7 or an 8 or a 9. So that's 4 ways. So the first digit has to be one of those 4 numbers. So we've taken care of the greater than 600,000 condition. The other big condition is that the number has to be odd. But it can be repeated. So no matter what I chose for the first digit, I can reuse it again, so that's not an issue. But for the number to be odd, it has to end, in other words, the units digit, the rightmost digit, has to either be a 1, 3, 5, 7, or 9. That's how I tell if a number is odd. I look at the units digit and see if the units digit is odd. So there's 1, 2, 3, 4, 5. There are 5 odd digits, so I can choose that to be any of those 5 odd digits because I can repeat. So even if the first digit was an odd, I could reuse it. Okay, that takes care of the first and the last digit. In the middle, the digits may be repeated, so no matter what I've chosen for the first and the last, I can reuse anything in the middle because they can be repeated. And there's nothing in the problem that says anything about the middle digits. So I can choose any of the 10 digits for the 4 middle digits. So by the fundamental counting principle, the number of ways to take a 6-digit number that has to be greater than 600,000 odd with repeated digits allowed is 4 times 10 times 10 times 10 times 10 times 5. That's 200,000. So there are 200,000 different ways to do this. Just to emphasize how this works, let's do another one. This time we're doing 3-digit numbers. How many 3-digit numbers can be formed using the digits 9, 6, 8, 5, 2, 1, and 7? In other words, not all 10 of the digits. We, for instance, can't use a 3, can't use a 4. We can only use 9, 6, 8, 5, 2, 1, 7. But they can be repeated. They can be repeated, so we can use them again. We're still choosing 3 digits, though. It's not a 6-digit number this time. It's a 3-digit number. So by the fundamental counting principle, it's the number of ways to choose each digit, all those subtasks multiplied together. Well, we can reuse the digits, but there are only 1, 2, 3, 4, 5. There are only 7 of them. So the first choice, I can choose any 7. I can repeat it, though, So there's no reason I can't use any of the 7 for the second digit or the third digit. So the total number of ways I can write down a 3-digit number using the digits 9, 6, 8, 5, 2, 1, 7, if I can repeat digits, is 343. So 343 ways to do that. What if I do the same problem but I don't allow repetition? So I've still got a 3-digit number. I'm still using 9, 6, 8, 5, 2, 1, 7, but this time I'm not allowing repetition. What happens? Well, the setup is the same, but this time I'm starting off with 7 digits, but I'm not allowing repetition. So in the beginning I can choose any of the 7, but once I choose one I can't reuse it. So I only have 6 ways to choose the second digit because I can't repeat. Now once I've chosen the first and second, then I only have 5 ways to choose the third digit because I can't repeat whatever I chose for the first one or the second one. So by the fundamental counting principle, there are 210 different ways that I can write down a 3-digit number using the digits 9, 6, 8, 5, 2, 1, 7.